Welcome to Learning with Ms. H. Today we're going to go into Earth Science and the Structure of Earth lesson. So this one is a super short lesson itself, but you do have some notes to take with it. So you're going to start off by doing your bell work. So if you haven't gotten your stuff together for it, go ahead and pause me, grab your notebook and something to write with, and then work on your bell work here and come back. The bell work itself is just to let me know or write down what you already know about the structure of the Earth. So there's some suggestions here for how was it made, what events created the features, what are the layers. Basically anything you know about Earth's structure can go here. As little or as much as you can think of. When you're done, come back and we will work on notes. All right, welcome back. We have notes, and then at the very bottom down here, you have this Layers of Earth homework assignment. This is one of those NADA quizzes. So it's a couple questions for you to answer. You can do it as many times as you need to. Go through the notes, answer this homework, and then you're done for the day. So let's take a look at the notes then. We're going to go to the center of the Earth here. From the outside in, we've got 4 layers: the crust, the mantle, the outer core, and the inner core. They used to think that there were only 3 layers: crust, mantle, and the core, and they've now discovered quite a few years ago actually that the outer and inner core are 2 separate things. So we actually do have 4 layers to the Earth. If you can't remember crust, mantle, outer, inner, you can use the mnemonic device, Carol made orange ice cream. A mnemonic device means that the first initial of the phrase you remember is the same as the first initial of each word that you're trying to remember. So crust is on the outside, and as we work our way in from there, we have mantle, outer core, and then finally at the very center of the Earth is the inner core. As always, if I go through these too fast, remember that you can pause the video, finish your slide, and then come back again, restart the video there to join us. So we're going to talk about each layer on the next few slides. We're going to start off with the crust, and we're going to work our way in towards the center. Now the crust is our thin, solid top layer of the Earth. It's the layer that encases everything. It's what we walk around on. If you think of it as a pie, the pie crust would be the same as the Earth's crust. It holds everything in. It is made up of 2 different types of rock. Underneath the ocean, you have basalt rock, and underneath the continents, you have granite rock. We're going to focus on those 2 types of rocks in a future unit when we start talking about rocks and minerals specifically. For right now, you just need to know the 2 types that exist and where they're found. So basalt in the oceans, granite in the continents. The temperature of the crust, anywhere from 15 degrees Celsius on the surface all the way down to 1,000 degrees Celsius at the bottom. So if you're looking at these temperatures, 15 degrees Celsius is approximately 60 degrees Fahrenheit. That's our average temperature, and 1,000 degrees Celsius is a little bit over 1,800 degrees Fahrenheit. And then it just gets hotter the deeper we go into the Earth as we travel towards the core. So the depth of the crust is anywhere from 0 to 40 kilometers. The thinner crust is going to be under the ocean. The thicker crust is going to be under the mountains. Density of the crust averages out to be about 3 grams per kilometer cubed. So not very dense at all. We're going to take a look at each of these 2 types of crust next. Continental is the land crust. That's the continents that we walk around on. It averages about 40 kilometers thick. It is, of course, thicker underneath the mountains than it is under the valleys, but 40 is the average. It has to be thicker under the mountains because they are basically giant rock piles, and they are super heavy, and the heavier they are, the more they push down, and the more structure they need underneath them. Oceanic crust, that's our sea floor. It is very, very dense rock, like basalts. It's a lot thinner than the continental crust. It averages only about 7 kilometers thick. And it is, however, super dense, so that's why it can hold all of the water and stand up to that pressure. You can see some of these basalt columns that form under the ocean. Not very many places, but there are a few places. Basically, if there's somewhere that used to be under the ocean that is not anymore, that's where you're going to find them. One of those locations is Giant's Causeway. This image is from the Ireland side of the Giant's Causeway, but it actually stretches from Northern Ireland all the way to southern Scotland, across the channel there. And what you're looking at here, these are giant basalt columns. So each one of these little layers is a layer of basalt that was thrust up into the ocean on the ocean floor, and then the cool temperatures of the water caused this basalt to solidify very, very quickly. And it solidifies in a hexagonal shape because it's so structured and orderly in its crystal structure. This area is called the Giant's Causeway because when it was first discovered, the people who found it thought it looked like a stairway for giants. So each one of these columns is a basalt column. So this is Oceanic Crust right here that you're looking at. Looking at it from the top down, this is the view that you get, and you can really see that hexagonal structure to it where they cooled off very quickly. So each one of these little hexagons is a layer of the ocean floor pushing up. This is the Atlantic Ocean back here, and the tide does still come in and cover some of this, but much of this is actually open to the public it's a national park area. So you pay your admission fee and you can go climb around on it, and it's really kind of a cool place. But the water levels of the ocean are going to fluctuate. So some parts of this will actually go underwater at high tide. It did used to all be underwater when the ocean levels were a little bit higher. And of course, ocean levels fluctuate over time with glaciers freezing, melting. The ocean levels will rise and fall. The next layer down is known as the mantle. It's called the plastic layer. It doesn't mean plastic like the hard plastic you would have as like a container or to make flashlights or any other objects with. It's plastic meaning pliable or moldable. So it's almost like really thick peanut butter, or if you've ever had Laffy Taffy, you can stretch that and pull it, and you can fold it and mold it together. That's the kind of material that makes up the mantle. It contains oxygen, silicon, and magnesium, and the temperatures here at the top of the mantle are that same 1,000 degrees Celsius that's the bottom of the crust, because they meet right there. And then as you go deeper into the mantle, it goes all the way up to 3,700 degrees Celsius. The depth of the mantle, it goes from 40 kilometers deep all the way down to 2,900 kilometers deep. And the deeper you go, the higher the temperature and the pressure gets. The density of the mantle could be anywhere from 3.3 to 5.5 grams per centimeter cubed. Remember, the crust was kilometers cubed, so the mantle is much more dense. And density is also going to increase the further down you go. So as you get deeper into the earth, you get increases in temperature, pressure, and density. The mantle has several layers to it. The top layer of the mantle combines with the crust to form what's known as the lithosphere. The lithosphere is a rigid area. It's basically our tectonic plates. So all of those puzzle pieces that are broken apart, that float around and make the earth have its shape and move our continents around, formed up Pangea, broke Pangea apart, gave us the continents we know today. All of those plates, those individual puzzle pieces, those are tectonic plates, and those are made up of this lithosphere. The lithosphere is going to float around on the next layer of the upper mantle, which is actually the asthenosphere. So it's underneath, and this is the part that you recognize as magma or lava. It's magma under the surface, lava once it comes out onto the surface. But this is the part that gives us all of the material for volcanic eruptions. It's the reason we have earthquakes, because this is shifting and moving, and it only moves as fast as your fingernails grow, so it's very, very slow moving. but it's got just enough that it can cause those shifts and movements in the rocks above. The lithosphere floats around on top of this asthenosphere. And this is a solid rock that flows. So again, that really thick, not really a solid, but not quite a liquid yet. All right, the next layer is the Mesosphere. This is the bottom part of the mantle, and it's solid. So you have solid crust, the flowy part of the mantle, and now we have another solid part of the mantle. And you'll find that our layers kind of sandwich themselves like that. So you have solid, liquid, holds everything in place. So this is the largest part of the mantle, and this is the part that goes all the way down to the Earth's core. We've got an image over here where it's got the mantle broken up into its physical sections. So the physical barriers where you have the different type of material, the solid lithosphere, the molten asthenosphere, the solid mesosphere, and then liquid outer core, solid inner core. Over on the right-hand side, though, you have the chemical breakdown, which is just the crust, the mantle, and the core. So that's the 3 layers. I would jot this image down in your notes so that you are aware of it and you have it in case you need it for the test. You'll see this image again on the last slide if you don't get it down now. So the next one is the outer core. And the outer core is a liquid layer and it flows around the inner core. These are going to spin or flow in opposite directions. So the liquid layer goes one direction and the solid layer spins the other direction. This bidirectional flowing of materials is actually what causes our magnetosphere to form, and we'll talk about what that gives us coming up. So it's made up of mostly iron. There's a little bit of nickel, not a whole lot, but there's some. It is mostly iron here. And again, it is liquid, so it flows. The temperature starts at the upper barrier of the outer core. The upper limit is 3,700 degrees Celsius. And then as you get deeper down into the earth towards the bottom of the outer core, it goes all the way up to 4,300 degrees Celsius. 4,300 degrees Celsius is about 7,700 degrees Fahrenheit. Ridiculously hot. The depth here starts on the upper limits at 2,900 kilometers deep, goes all the way down to 5,200 kilometers deep, and the density goes from just under 10 to just over 12 grams per centimeters cubed. After the outer core, you have the inner core, and this is the very center of the Earth. This is the heart of the Earth. It is solid, super dense, and about the size of the moon. It is almost all iron. There are some little bits of nickel in there, but it's almost all iron at this point. This is as hot as it gets here on Earth, and the temperatures are about as hot as the surface of the sun, anywhere from 4,300 degrees Celsius all the way up to 6,000 degrees Celsius at that very center. It goes from an upper limit of 5,200 kilometers to a very middle of the inner core, 6,378 kilometers, and a density of just over 12.5 to 13 grams per centimeters cubed. We talked about that magnetosphere. So some of the core interactions that we have are the spinning of the cores in the opposite direction. The outer core goes from east to west. The inner core goes from west to east, and as they pass over each other, they're going at different speeds in different directions, and that causes that magnetic field to form. And the reason that's important is it's basically what allows us to live here on the planet. So it gives us our protection by deflecting the solar radiation and the wind, so it protects us from all the bad stuff from the sun. It also allows compasses to point north by creating that magnetic field, and some believe that it actually allows us to use our electronics. This is a quick reference on density. You get more dense the deeper you go into the Earth. Same thing's going to happen for temperature and pressure. You have the surface up here at the top, temperature increasing to the right, depth is increasing down over here on the left. So as we go down, we get hotter. Mapping the Earth's interior, the way that we know what the rock is made of is from something called seismic waves. We have P waves and S waves that travel through the earth whenever an earthquake happens, and we can measure those. They're going to move faster through a solid rock than a liquid, kind of like if you're running on the ground versus trying to run in a pool. And they can map those distances and how long it takes the waves to reach different locations in order to figure out what kind of material they're passing through. All right, so again, quick review, temperature, pressure, and density are all going to increase the deeper you go into Earth. And then you have a couple of images here that you can copy down into your notes so you can be aware of the different layers and how it all fits together. And when you're done with this, work on your assignment and you are done for the day. We'll see you next time.